In our last video, we introduced the idea or concept of periodic waves, something created by a periodic disturbance. We also talked about different things we can measure about those periodic waves, like the wavelength, the frequency, the amplitude, and the period. Well, we're going to start investigating how those different measurements are related to one another and how they affect one another. So let's take this periodic wave. It has a random amplitude of about 3/4 of a centimeter. It's moving up and down at a speed so that it makes about 1.5 cycles each and every second. And let's go ahead and find out what the wavelength of this periodic wave is. We can measure, remember, from crest to crest or from trough to trough. So if we just go from crest to crest, it looks like this has a wavelength of about 2.5 centimeters. Well, one question we could ask is, what affects the length of the wavelength? Like how far apart crests are from one another or troughs are located from one another? Well, what are some things that we could change? We could change the amplitude. Let's make it a larger amplitude and hit play. You can see that each part of the material, as the periodic wave moves through the material, is getting displaced farther from equilibrium. If we pause this, we measure the wavelength. It looks like the wavelength is about 2.5 centimeters. It's about the same. So it looks like the amplitude didn't change things at all. Let's try a little bit lower amplitude. We'll pause it. And we can see that the wavelength from crest to crest is, again, about 2.5 centimeters. So the amplitude doesn't seem to affect the wavelength. How far apart the crests are located from one another or the troughs are located from one another. Well, what about frequency? I'm going to turn the amplitude up a little bit. And I'm going to reduce the frequency. So it's making less cycles each and every second. You see, as the frequency goes down, what happens to the wavelength? Well, it seems pretty clear the wavelength is much, much larger. If we pause it, we can see that the wavelength, in this case, from crest to crest looks like it's almost about 7 centimeters. So it seems like frequency has a very big effect on wavelength. If we increase the frequency, as the frequency goes up, notice that the crests are now spaced closer and closer. In this case, it's about 1.2, 1.3 centimeters. As the frequency increases, the wavelength goes down. And as the frequency decreases, there's less cycles each second. Looks like the wavelength is increased. So the question that you guys are going to work on answering is, how is the wavelength and the frequency of a periodic wave related to one another? How are they graphically related, and how are they algebraically related to one another? So to answer that question, you guys are going to go through an investigation looking at how wavelength is related to frequency, like we've done throughout the year in other investigations. So you're not going to write a formal lab report, but we're going to go through the same process as we would for a formal investigative lab to figure out how these two things are related. So we're going to call this the wavelength versus frequency lab. And every one of our investigations starts with a purpose statement. So here's ours. Our purpose will be to determine the relationship between the wavelength of a periodic wave and the frequency, which is the number of cycles each second. Well, in order to do the lab and collect the data, we're going to use the simulation that we've been looking at and using called waves on a string. So you guys can change the frequency quantitatively and then quantitatively measure what the wavelength of that periodic wave actually is. So one quick note about data collection. Remember, you can easily change the frequency just by moving the slider back and forth, and it's going to tell you quantitatively what the frequency is. And if you pause it, we can measure the wavelength. Now, this is one where the wavelength is easy, right? We either measure from crest to crest or we measure from trough to trough, and we should be able to get the same measurement. But let's find out what happens. Let me move the frequency so it's like a really low frequency. And let me pause it. Yeah, let me make it a little bit lower. Okay, I'll pause it right here. Well, notice we've got a really big wavelength. The wavelength doesn't fit within the simulation, so how do we figure out what one full wavelength is? Well, think about how much of a wave do we actually have in front of us? Well, it's less than a full wavelength. But let's look at, let's say, from this position to this position. So it goes from equilibrium up to a crest down to equilibrium. Well, how much of a wavelength is that? Well, remember, for a full wavelength, that has to go from equilibrium up to crest down to equilibrium. Then it has to go through a trough back to equilibrium. And so from equilibrium here, let's say put it at 0, all the way down to where it reaches equilibrium next. That's not a full wavelength, that's a half a wavelength. So in this case, we've got a wavelength that's about, looks like about 5.6 centimeters. And so just multiply that by 2, you get about 11.2 centimeters. So your wavelength would be 11.2 in this case. So when you guys make a data table to write down the data that you collect, my suggestion is make at least 3 columns. So we're going to have one so you guys can write down the frequency that you use. Remember, you can just move that slider back and forth to figure out exactly what the frequency is quantitatively in hertz or cycles per second. And frequency is the units for frequency is hertz or cycles per second. And another way to represent that is just inverse seconds. It's so many cycles per second or oscillations per second or events per second. And so we can just shorten it as inverse seconds or 1/seconds. For each frequency, I want you guys to measure what the wavelength is. Just use the ruler in the simulation, and that's going to be measuring the wavelength in centimeters, and we'll just leave it as that. And I want you guys to add an extra column in case you guys need to linearize your graph. So once you get your data, we're going to go through the same process of data analysis as we have in all of our previous labs, and so we're going to graph the 2 variables. Find out, how, first of all, how they're graphically related. When you get to this point, I want you guys to put the frequency on the x-axis, measured in inverse seconds, and the wavelength, or lambda, measured in centimeters on the y-axis. You can go through the same process. You're going to find out how they're graphically related. If it's not a line, remember, so that we can get an equation to show how these things are related, you guys are going to have to linearize that graph. And then you're going to write the equation of whatever linear graph you have. And once you have that equation, you're going to think about what the slope represents and evidence for that and the significance of the y-intercept. Remember, if you have to linearize your graph or re-express it, this is kind of how you do it. So you can come back to this part in the video if you don't remember to figure out how to do this. So these are the different shapes or the types of graphs we typically find when we do investigations in nature. And below we'll show you what you have to do or graph to re-express that graph to make it appear linear so that you guys can write the algebraic equation for how wavelength and frequency are related to one another. One last thing before you guys start data collection. I want you guys to choose either using low tension when you guys are collecting your data and just keeping it on low tension to find out how frequency and wavelength are related to one another, or you can choose medium tension, or you can choose high tension. And remember, back in one of our previous investigations, we found out that changing tension changes how fast the waves actually move through the material or medium, or the string in this case. And so choose either low, medium, or high, and then keep it at that tension for your whole data collection. Okay. Have fun collecting data.